Good morning. In the last recording, we finished acetylcholine. Now let's continue the discussion of neurotransmitters. Now we're going to start talking about monoamines or biogenic amines. These are the group of neurotransmitters that they are derived from one amino acid. But before we talk about this one, let's review something basic about anatomy of the brain. This is an intact brain. This is the front of the brain. This is the back of the brain. This is cerebellum. And if you continue, this one is going to go to the spinal cord. If I cut this brain and create right and left halves, so I'm going to cut it right in the middle and remove this section. That's what you're going to see. This is the right side of the brain. This is the same as this one. This is a real one. This is a drawing one. So I just want to make sure you understand different part of the brain before we continue this neurotransmitter. This part of the brain that you see I'm pointing to, this is called cerebrum. This part of the brain is called cerebellum. This part of the brain that I'm pointing to, this one, is called diencephalon. And from here to here, this piece is called brain stem. Diencephalon is composed of some structure that has the name thalamus. So anything with the name thalamus belongs to this structure here. For instance, this is a thalamus, this is hypothalamus, this is epithalamus. And brainstem, which is here, is composed of three pieces. This piece from here to here, this one, is called midbrain. This part is called pons, and this part is called medulla oblongata. So now, knowing this one, let's start monoamines. Monoamines, as I said, is derived from a single amino acid. There are two groups, catecholamines and indolamines. Catecholamines are a group of neurotransmitters that are derived from tyrosine. Tyrosine is an amino acid. Catecholamine composed of dopamine, norepinephrine, and epinephrine. Indolamine, on the other hand, is composed of two neurotransmitters, serotonin and histamine. Serotonin is derived from tryptophan, and histamine is derived from histidine. If you look at this picture here, you can see the amino acid phenylalanine is going to change to another amino acid called tyrosine. Tyrosine later is going to change to dopa. Dopa is going to change to dopamine. Dopamine is going to change to norepinephrine. And finally, norepinephrine produces epinephrine. Clearly, each one needs a specific enzyme. For your class, I won't ask you the name of the enzyme. It's not necessary for you to know. In biochemistry, you're going to memorize it anyway. However, some neurons, they release dopamine. They don't go beyond this point. Why? Because they don't have these enzymes. Some neurons release only norepinephrine. They don't go to epinephrine. Why? Because they don't have this enzyme. And finally, some cells produce epinephrine. Those neurons that release dopamine are called dopaminergic neuron. Those neurons that release norepinephrine is called adrenergic neuron. And those cells that release epinephrine, they're located only one place, and that is in the adrenal medulla. The medulla of adrenal gland releases epinephrine. We're going to get to this one also. So for now, remember, dopaminergic neuron releases dopamine, and adrenergic neuron releases norepinephrine. This is the first neuron. Here's the second neuron. Like the same story we said about acetylcholine, at the end of the neuron, we have vesicle full of norepinephrine. When the action potential reaches here, the same process that we explained for the acetylcholine happens here also. Calcium is going to come in, attaches to the calmodulin, and the rest of the story that you know. At the end of the day, we're going to release norepinephrine as a neurotransmitter. Norepinephrine is going to sit on the receptor that is located on the cell membrane of the postsynaptic cell and carries on the effect. We have to take this norepinephrine away from this receptor. Otherwise, norepinephrine continues stimulating this postsynaptic cell. How do we remove this neurotransmitter? Well, the answer is there are two ways. One is we can reuptake this norepinephrine back inside the cell. Inside this presynaptic neuron, we have an enzyme, it's called MAO is called monoamine oxidase, and monoamine oxidase is going to break down norepinephrine through oxidative deamination. There is another way to destroy this norepinephrine, and that is there's an enzyme, it's called COMT, is catechol O-methyltransferase. This enzyme is a methylating enzyme. The most important enzyme is monoamine oxidase, and as we said, is found inside the presynaptic neuron. Catechol O-methyltransferase is not found inside the presynaptic neuron, but is found in the synaptic cleft and so many other areas. For instance, you can find it in the liver, you can find it in the blood circulation, in the smooth muscle, and also in the kidney. All these monoamines that we talked about, they use second messenger. In other words, they don't use a direct ion channel, the one like nicotine receptor, that the channel and receptor the same thing. Monoamines use second messenger. The most important second messenger we mentioned is cyclic AMP. So let's start with norepinephrine as a neurotransmitter. Probably the second most important neurotransmitter in our body is norepinephrine. Norepinephrine is found in the CNS, means brain and spinal cord, and in the PNS, in all other nerves outside the brain or spinal cord. In the CNS, norepinephrine is responsible for arousal. It's going to make you more alert. Amphetamine also is going to stimulate the pathway of norepinephrine. In other words, it has a similar function. Let's see how norepinephrine works. Norepinephrine is going to sit on the receptor. This receptor is not a channel. As you can see, channel is here. When norepinephrine sits on the receptor, again we're going to deal with G protein. The same story we said about G protein in the case of muscarinic receptor. When the norepinephrine sits on the receptor, G protein breaks down. This time, the alpha subunit is going to move, and it's going to attach to this enzyme. This is a protein that is found in the cell membrane, and this enzyme is called adenylate cyclase or adenylyl cyclase. Adenylate cyclase is inactive. When alpha unit attaches to it, becomes active. You must know the action of this enzyme, and this is the enzyme that breaks down ATP and creates cyclic AMP. So this enzyme breaks down ATP to create cyclic AMP. Now cyclic AMP is a second messenger. Cyclic AMP activates a protein kinase inside the cell. This protein kinase is inactive. The presence of cyclic AMP activates protein kinase, and protein kinase is the one that comes to this ion channel and exchange phosphate and change the position of this channel. In the case of norepinephrine, channel was closed, and protein kinase, by giving phosphate to this channel, is going to open it up. So this ion channel is going to open because of the phosphorylation of the channel. In the brain, the neuron that contains norepinephrine, they are located in areas called locus coeruleus. This locus coeruleus is located in the rostral part of the pons. Rostral means upper part of the pons. If you remember, this is the pons, and here's my locus coeruleus. So it's between the pons and the midbrain, and majority of the neuron in this area, they contain norepinephrine. The neuron from locus coeruleus, they're involved in arousal, behavioral arousal. Norepinephrine can be excitatory or can be inhibitory. Depends on what type of receptor they have. We don't use it very often today. In the past, one of the way we treat the people to overcome depression was increasing norepinephrine in the brain. How do we do that? If you block MAO by MAO inhibitor, then the amount of norepinephrine will increase. Therefore, we could improve the people's depression. Today, we don't use it because this type of drugs, they have a lot of side effects. But one thing is interesting for you to know, that people who take monoamine oxidase inhibitor, they're supposed to be refrained from any food that contains tyramine. Tyramine is natural chemical that you may find it in the certain cheese, especially old cheese, and also beverages like red wine. Tyramine is going to release a lot of catecholamines from the vesicles. So imagine if someone is taking MAO inhibitor and eating lots of red wine or old cheese, then the amount of norepinephrine in their synaptic cleft would go very high, and these people, they're going to show a lot of side effects of too much of norepinephrine. With the same token, we mentioned a few minutes ago that amphetamine also is going to have similar effect of norepinephrine. Therefore, amphetamine is considered as a psychostimulant, and we use amphetamine in medicine for people with ADHD or with narcolepsy. We can also use amphetamine for a short-term weight loss because it's going to increase your metabolism and it's going to increase your level of activity, and as a result, people, they're going to lose weight. With the same token, cocaine inhibits the reuptake of norepinephrine and dopamine. As a result, cocaine is going to increase norepinephrine in the brain and in the peripheral and make the patient to become very aroused and agitated. Monoamine oxidase and COMT, each one can break down any of these products, dopamine, norepinephrine, or epinephrine, but also they can do it together. In other words, you can break down dopamine through MAO or through the COMT, or you can do it with combination of this one in any order. Each one is going to have a metabolite. This metabolite is going to appear inside the urine. The most important metabolite that you need to know for norepinephrine would be normetanephrine. The most important metabolite of epinephrine that you need to know is metanephrine, and the most important metabolite of either norepinephrine and epinephrine as a result of the function of the both would be VMA. VMA stands for 3-methoxy-4-hydroxymandelic acid, and that is going to bring us to the serotonin. Another name for serotonin is 5-hydroxytryptamine or 5-HT. That tells you that serotonin is derived from tryptophan. Tryptophan is going to first change into 5-hydroxytryptophan, and then it's going to change to 5-hydroxytryptamine, which is the same as serotonin. The neuron that releases serotonin is called serotonergic neuron, and you can find this neuron not only in the brain but also in the GI tract. In the brain, the most common area that you can find serotonin would be in the RAF nuclei. RAF nuclei is in the middle region of the brainstem. So it's going to continue from upper part of the brainstem, which is midbrain, all the way to the medulla. So these are called RAF nuclei. The ascending fiber from RAF nuclei goes to cerebral cortex and is involved with sleep mechanism. The descending fiber that is going to go down to spinal cord is involved with modulation of pain. Serotonin is a very challenging neurotransmitter because serotonin has so many different functions, from mood to behavior to appetite to cerebral circulation. Why there are so many functions of serotonin? Because serotonin has over a dozen different types of receptors, and you can imagine with that many number of receptors you can have many different functions. A drug like LSD or any other hallucinogens, they are agonists for serotonin receptor. We have a list of drugs that they block reuptake of serotonin. As a result, serotonin will increase inside the synaptic cleft and create more effects. We use serotonin specific reuptake inhibitor or SSRIs to fight against depression. The drugs like Prozac or Zoloft, those are drugs commonly used for depression. Serotonin also uses second messenger, except one type of serotonin receptor is called 5H3 subtype, and that is the one that has a direct coupling, just like nicotinic receptor. So the rest of the receptor for serotonin, they use second messenger except the subtype 3. Subtype 3 is always stimulatory. After serotonin is being released, there is a few destinations for this serotonin. It can be reuptake intact inside the neuron and goes back to the vesicle, or it can be degraded and turn into 5-hydroxyindoleacetic acid. Abbreviation of that one, it would be 5-HIAA, or they can be retrieved and go to the pineal gland and is used to produce melatonin that is going to deal with sleep process. As a side note, I want to tell you that we use SSRI for treatment of anorexia nervosa as well. Remember, serotonin deals with appetite as well. This is a long story. If you're interested, you can read about this one online. I think it would be fascinating. Now let's change the gear and talk about dopamine. Dopamine as a neurotransmitter is a very sophisticated and very important neurotransmitter. The neurons that release dopamine is called dopaminergic neuron, and in the brain they are concentrated inside the midbrain. There are two main systems that use dopamine. One is called nigrostriatal system, another is called mesolimbic system. Nigrostriatal system involves with motor control. Mesolimbic system involves with emotional reward. What does that mean? Let's take a look. I want you to follow this blue and red one. Let's start with the blue one. This part of the brain is called substantia nigra, is in upper part of your midbrain. Substantia nigra is a nucleus. It's composed of a bunch of cell bodies. The axon of this cell body is going to come to another part inside the diencephalon, which is called corpus striatum. We're going to talk about corpus striatum. If you don't know what it is, don't worry about it. Some students, they get very scared by all these big names. Let me tell you something. These are just a bunch of names. It shouldn't be scary to you. Slowly you're going to get comfortable with these names. Just remember, there's a structure inside the brain. It's called substantia nigra. And what is substantia nigra? It's a collection of the cell body. Every cell body should have an axon. The axon of this cell bodies move and it's going to come to another part of the brain. It's called corpus striatum. Since this neuron is going to start from the substantia nigra and goes to corpus striatum, we call this pathway, we call this system, we call it nigrostriatal system. This system is going to help you to coordinate and initiate your muscle movement. Remember Parkinson's disease? These people, they cannot control their muscle movement. They are shaking because this system is dying. The neuron that releases this dopamine and it starts from the substantia nigra and bring dopamine to corpus striatum is dying. So when the cell body is dying, you release less dopamine, and the result of this one is called Parkinson. Another system that is super important and is deal with dopamine is the one that starts from part of the brain. It's called VTA, ventral tegmental area. VTA is part of your midbrain. The neuron from here is going to continue and is going to go to another area which is next to corpus striatum, and that is called nucleus accumbens. So this neuron starts from the VTA and the axon is going to go to nucleus accumbens, which is in proximity of the corpus striatum. Nucleus accumbens is responsible for pleasure and reward. Therefore, this system is going to deal with reward, pleasure, addiction, laughter, and fear. Anything that deals with your emotion. The picture is kind of misleading also because VTA, it starts from the upper part of midbrain. So it shows inside the encephalon, but in reality it's in the upper part of midbrain. Many people, they're addicted to alcohol, gambling, smoking, because this system is very active. Schizophrenia also is associated with too much of dopamine in this system. When we treat schizophrenia, we are trying to decrease dopamine in their mesolimbic system. Psychostimulants like cocaine and alcohol, amphetamine, marijuana, morphine, or nicotine, they all directly target VTA. Although we mentioned two systems for dopamine, but in reality there are more systems in the brain that deals with dopamine. There are three more that I like you to know because we're going to talk about these three later in more detail. One is called mesocortical system, another one is called tuberoinfundibular system, and the third one is called chemoreceptor trigger zone. Mesocortical system also is going to deal with emotional reward, just like the mesolimbic system. As you can see in this picture, some of this red line is going to start from VTA, but instead of going to the nucleus accumbens, it's going to go to prefrontal cortex. As you know, frontal lobe is dealing with your behavior and your character. This system attaches your VTA to frontal lobe. In other words, your behavior also is going to be affected by this system. So let's say you enjoy things because of mesolimbic, and then you do things because of mesocortical system. You enjoy gambling, and then you have a strong drive to go to the casino and play. You feel so good when you drink, and as a result, there's going to be impulse. There's going to be a force in your body and says, okay, let's go and drink. So as you can see, your feeling and your behavior are so related to each other because both systems, they start from the VTA. Some is going to go to nucleus accumbens and some is going to come to prefrontal cortex. The one that goes to the nucleus accumbens is called mesolimbic, and the one that comes to the prefrontal cortex is called mesocortical. Tuberoinfundibular system is a system that starts from hypothalamus and goes to the pituitary gland. Remember, this area is a hypothalamus and this one is a pituitary gland. There are some neurons that it doesn't show in this picture. It starts from here and goes to pituitary gland. This neuron that starts from here and goes to pituitary gland also they release dopamine. This system is called tuberoinfundibular system. We're going to talk about this one later in the endocrine system. The function of this system is decreasing the release of prolactin. Prolactin is a hormone that makes you to produce milk. As a result of this system, your milk production decreases. And finally, we have a system, it's called chemoreceptor trigger zone, or it's called CTZ. This center, this zone, is responsible for vomiting. When you activate this center with dopamine, that is going to make you to vomit. As a result, one of the great strategy to stop vomiting in people who go through chemotherapy is giving them a drug that blocks D2 receptor of the dopamine. As a result, these people, they don't vomit. I'm sure many of you remember years ago, one of the huge side effects of chemotherapy was vomiting of the patient. They didn't want to go through chemotherapy because of this huge side effect. Today, it's not that important because we have great drugs that blocks this emesis center. One of them is through blocking D2 receptor. And that is going to bring us to the end of this part 2 of chapter 7. I'm going to get back to you with the last part of this one very soon.